Hello everyone, today I want to share the literature review on Hindsight Experience Replay. This paper proposes drawing a sampling or a trajectory construction scheme for reinforcement learning. And since I'm working on transit control with reinforcement learning recently, so I will review multiple papers about reinforcement learning these days. Now let's begin today's literature review. The review will be included 3 parts. The first is the motivation. The basic target of this paper is to deal with the sparse reward in reinforcement learning problem. As you can see, this robot wants to put this box to hit a target, and he cannot receive a positive reward only after he put this box hit a target. So this procedure presents a very sparse reward feedback. As a result, the training will be very low efficiency. And the current studies to deal with sparse reward is the reward shaping, and there are some major limitations. First, the reward function engineering is difficult, and the reward shaping has limited applicability due to the requirement of domain knowledge. To fill this gap, this paper proposes a very brand new idea to deal with the sparse reward problem. The major advantages of the proposed method will be threefold. The first is that it can improve sample efficiency. The second is that the method makes learning possible even with sparse or binary reward signal. And last but not least, this method can fit with universal policies training scheme. Now, before we dive into the methodology, let's come to the background of the reinforcement learning. As you can see, in the domain of reinforcement learning, the most important part of this algorithm is to get the exactly Q value of the research problem. The Q value indicates that as state X, when the engine is located in state X and he chooses action A, what he will get in the what the reward he will get in the consider the long term. And in reinforcement learning problem, we will develop an algorithm to update the state action value iteratively by trial, and this is traditionally the update formula. And since the Q value, since in the past studies the Q value will be stored into a table, and it will each time it will update one of the entry of this table. That requires table that sometimes will require the table to be much large, and it will be a big problem for memory. So as the deep learning is proposed, the reinforcement learning is developed to a great extent. The DQ networks try to approximate Q value with neural network, and the training procedure will be implemented in the form of supervised learning on Q value. And the samples to be used to train for the DQ networks is the trajectories the engine has experienced during the interaction with the environment. And then trajectories will store in a buffer, and it will implement experience replay for batch sampling, which means that after storing some of the trajectories in a buffer, during the train procedure, the engine will sample some of the trajectories to add as a sample to train its parameters. And the other solution for reinforcement learning is to directly optimize the policy. And one of the most famous algorithm is the deterministic parser gradients. In this method, they use a cryptic neural network for value estimation, just very similar to the DQ network does. In addition, it uses actor neural network for parser optimization. Actor means that it is responsible for the action selection procedure, and his optimization goal is to minimize the minus Q expectation of Q value, and in other words, it directly optimizes the Q value with the gradient uh, gradient of the parser. In this way, the parser is a parameterized functions, which is represented by a neural network. And also there are some paper that is interested in multi-goal reinforcement, which means that there are more than one goal to achieve. And in this case, the Q value is not only based on the state and action at each time step, but also there is a given goal to indicate the quality of the Q value. And now let's come to the Hindsight Experience Replay. And before we go into the algorithm, we begin with a motivating example. This example is proposed by the paper to introduce the idea much more clearly. This example is the bit flipping, and what the problem describes is that given initial state as 0, this is the encode of this state, and this is the goal state the engine wants to achieve after a certain step of action. This is the goal state. Now the test is that the engine will flip length of x0 times for each episode to turn the initial state into goal state. And in this case, the initial state has 6 bits, so it means that we will flip the initial state 6 times, and then we see whether we can put this initial state to the goal state. And the procedure it will be presented in this picture. As for example, at step 1 we have an initial state as 0, and if we choose action equals to 3 here, that means that the third element of this state will be flipped, and this state will be turned into this state. Now at step 2 we will add, if we choose action equals to 1, then it means that the first element will be flipped, and in this time the first element will be flipped from 1 to 0. That's what this task want to. This is the description of this task. And after the 6 steps, we can get a final state. If the x6 does not match the goal state, which means that if we after 6 steps of flipping certain elements, the final state does not match the goal state, the reward will be -1. Otherwise, we will get a positive reward 1. And that's the overall problem of the motivating example. And as you can see, we only get meaningful reward in the end and have little chance to get reward 1, especially when the initial state becomes much larger. That means that we have little chance to make the initial state to match with the goal state exactly. So this is there is a too sparse feedback to train. That's the problem of that's the problem, and And in the reinforcement, and when we try to use reinforcement to deal with the problem in robotics problems, there is the main problem. The sparse reward really the sparse reward really hinders the training of the engine. And one of the idea of this paper is that let each step return a feedback without reward shaping. And the idea is that when we arrive state ST at step T, we should let the engine learn how to achieve state ST. In this way, we will not waste the trajectories and we can get a meaningful reward at each step instead of waiting for the final step to get a very sparse reward signal. That's what hindsight stands. The hindsight means that we get to the state, we know what we have understood what where we will arrive, and we let the engine learn how to arrive to that state instead of the goal state. There's no matter the arriving state is goal state or not. We just want to learn this state. We just want to learn how to arrive in this state. That's the basic idea of the Hindsight Experience Replay. And let's come to the algorithm of this methodology. At first, we can see that this method fit with existing the reinforcement algorithm. So when you use this scheme to train your engine, that means that you can use the state-of-the-art reinforcement algorithms. This scheme acts like a supplement of your original algorithm. And then we will implement M episodes to interact with the environment. At each episode, we will sample a goal and an initial state as 0. Why we have to sample a goal here? Because for multiple tasks, we will sample one goal each time to train the engine, because as the multi-goal reinforcement, the Q value is not only based on the state and action but also the goal. So we have to point out which goal we want to achieve. Especially for multi-goal task, we should sample a goal. Sample one of the goals in the multi-goal buffer. And then here is the interaction between the engine and the environment. The engine will interact with the environment using policy, whose input contains the state and the goal. And this is the parameterized policy. And the input of this function is the state concatenate with the sample goal, and the output of this function is the action. And this is the overall interaction structure and interaction procedure of the engine. And in this algorithm, it indicates T steps, which means that the engine will interact with the environment with a horizon of which means that it takes T time steps for the engine to interact with the environment, and then the engine can correct the trajectory with the maximum length of T. So after the interaction, at each time step, the engine will receive a reward, and then here comes the important part of this algorithm, which means that the engine will organize and store trajectories for further training. And this procedure includes two parts. The first part is that the engine store trajectory whose reward is based on the sample goal. This goal is the sample goal. which means that this is the actual target of this interaction, and this is the standard experience replay because what we want to learn is how to get the target gold. And the second part of this trajectory correction procedure is that the engine also stores trajectories whose reward is based on a customized goal. And in this part, the G point means that we customize a goal. This goal could be a state where the engine actually arrive, or any other goals you want to you have customized. In this way, the motivation is to let the engine learn additional goals to facilitate his learning, so the reward will not be very sparse for the engine. And here the G is used to customize the goal, and in this way the multi-goal setting is achieved. You can set as for example, you can the G point can be the state the engine has actually arrived, and then the engine will learn how to arrive at this state, and that's the that's the most critical part of the Hindsight Experience Replay. And then the training procedure will sample from the replay buffer. The replay buffer is formed in this procedure. Now let's come to the empirical study. There are 3 tasks the paper research. The first is the pushing. In this task, a box is placed on a table in front of the robot, and the task is to move it to the target location on the table. The second is sliding. In this task, a puck is placed on a long slippery table, and the target position is outside of the robot's reach, so they have to hit the puck with such a force that it slides and then stops in the appropriate place due to friction. And the last task is pick and place. This task is similar to the pushing, but the target position is in the air, and the figures are not locked. So the empirical study presents several problems, and there is experiments to answer these problems. The first is that, does HER improve performance? Among 3 tasks, the HER presents the best performance compared to the current algorithm, especially the DDPG. The second is that, does HER improve performance even if there is one goal to care about, which means that if there is not a multiple goal task but just one goal, and since the HER can customize goal distributions, have a customized goal, so it can turn the single code task to multi-goal task to train the engine. In this way, this experiment also demonstrates that this scheme is helpful, and learning multiple goal is better than learning one goal for the engine to deal with a certain task. And the third question is that, how does HER interact with reward shaping? And what the author want to point out is that the reward shaping performs poorly because mainly for 2 reasons. The first is that there is a huge discrepancy between what we optimize and success condition. In my view, this opinion means that the high requirement of domain knowledge in reward shaping is will make this reward shaping performs poorly. The second is that the shaping rewards penalize for improper behavior. Just like if you move to the box in a wrong direction, the shape rewards will give you a very bad feedback that will hinder the exploration, which will make the engine afraid of exploring any other policies because there will be a bad feedback by doing this. And the fourth question is that how many goals should be replayed each tragedy with and how to choose them. How many goals? This is related to this procedure. In this procedure, we customize code from this function, which all depends on the settings by ourselves, and this is a hyperparameter as pointed out by the paper. So in order to make this scheme suitable to a problem or make it much more efficiency, you should define the how large the G is and define the customized rewards. And this is the major task you have to deal with by yourself. Thank you for watching. Maybe the illustration is a kind of unclear, but I'm looking forward to your discussion, and let's understand the state of the art reinforcement learning much better after the discussion.